For thousands of years, in timber, in stone, in iron and steel, we have built. And for thousands of years, from the moment the first brick is laid, the first rivet is fixed, the first slab of concrete is poured, the processes of corrosion begin. We live in a world that is constantly breaking down. The elements of nature are constantly changing, reacting with each other, wearing each other down, corroding. Bridges collapse, bicycle frames crack, handrails give way, walls fall, engines fail, pipes burst, ships sink. This is corrosion. Constant, relentless, unforgiving. And yet we tame it. We control it so our buildings stay up, our bridges carry us safely, aeroplanes continue to defy gravity, engines continue to run, ships stay afloat. We control the corrosive effects of electricity, gases, and acids. The great works of mankind are possible only because we can control corrosion. Within a few years, even the greatest building and engineering projects are completed, and those who constructed them are gone. Then the corrosion engineers take over. Quietly, efficiently. So quietly and efficiently, in fact, that the process is invisible to most people. But without them, our world would be very different. Building the Eiffel Tower was an amazing feat of engineering, yet it was only ever intended to be a temporary structure. Keeping it in place for over 100 years is the real triumph. The Whyalla pipeline took a mere 18 months to build and is still resisting corrosion more than 60 years after it was laid. The fight against corrosion never stops. Corrosion doesn't just happen to metal. It can happen to everything, and it's happening all the time. Chemical interaction with its environment causes the deterioration of all materials, plastics, concrete and wood, and of course, metal. And the most widely used metal is iron. Iron ore is rust, corroded steel. The process of smelting merely turns it back into steel. But it wants to return to its true form. It wants to be rust. And rust never sleeps. There are almost as many forms of corrosion as there are things to corrode, but broadly they fall into some basic categories. General corrosion occurs whenever a material reacts with something in the atmosphere or water, rust in cars and boats, or when chemicals attack pipes or tanks. Galvanic attack happens where two different metals are in contact. One metal dissolves and leaves its noble cousin intact. Localized attack occurs in crevices such as washers or bolts, or as pitting. Stress and the wrong environment can lead to cracking. Hot, salty stainless steel and vibrating pumps are particularly susceptible to this form of corrosion. Erosion, abrasion, or cavitation occur where movement and corrosion combine to accelerate the breakdown of a material. Even the effect of microbes can accelerate corrosion. High temperature from gases or simply hot air can also cause corrosion. Clearly, if the thing that causes the corrosion can't get at the material you need to protect, it won't corrode. Putting in a barrier is a simple principle, and in most cases the simplest exercise to perform. We paint things to make them look good, but we also do so to protect them. So the right paint is crucial. And you need more than a color chart to choose it. But most often paint is not enough, and a more sophisticated liquid coating or lining is required, such as epoxy or polyurethane. In other cases, protective materials such as rubber and polypropylene is applied as sheets or films. All these methods require the surface to be prepared properly so it doesn't fail and come away, taking the protection with it. This often takes the form of abrasive blasting with grit or water, which is common on larger scale works. Dry ice is often used on aluminium aircraft. Pickling or hand tool preparation are appropriate on a smaller scale. Primers are often used to make sure the coating is firmly fixed. Elements in the galvanic table corrode at different rates. Those lower down the table corrode more easily. And when two materials are placed together, the one that corrodes more easily also corrodes first. This is the fundamental principle of galvanic corrosion and galvanic protection. Galvanic corrosion causes failure where there are aluminium rivets in stainless steel panels, steel bolts in stainless steel, or outboard motor carbon smut on an aluminium boat. Galvanic protection, on the other hand, is beautifully simple. If you attach a more easily corroded substance to the one you want to protect, the protected or galvanized material will last longer. Australia is a harsh country, one in which the things we use every day, such as our roofs, are constantly under attack from the elements. So it's little wonder that inorganic zinc coating was first developed in Australia. The zinc corrodes before the steel. Galvanized iron roofs eventually rust, but only when the zinc has corroded away first. Zinc can be sprayed on in a paint shop, applied through hot-dip galvanizing or electroplating processes, or even sprayed on as molten metal. Other metals are used as sacrificial coatings, but zinc is the most common. It's used everywhere from buildings to lampposts, power poles and trailers. Even nails can be galvanized to prevent them rusting. Instead of protecting something from corrosion, it may be cheaper in the long run to use a material that is more resistant. Stainless steel and titanium, or the copper-based alloys used in domes or seawater piping, are resistant because they form a protective oxide film. Alternatively, materials such as gold on printed circuit boards or nickel in strong acids like hydrochloric acid are simply inert. Stainless steel was invented almost by accident in World War I as a means of reducing wear in gun barrels. Several hundred different grades of stainless steel are now available for uses such as kitchenware, street furniture, chemical plants, boats, and in the food, chemical and pharmaceutical industries. Titanium, nickel, and other more resistant alloys are used in more severe environments. Corrosion involves the flow of electric current from the metal that is dissolving through the water wetting it. If an external current is applied, then the corrosion can be stopped. This is cathodic protection. The current is delivered by zinc, aluminium, or magnesium anodes, which are sacrificial. This means the anode corrodes, but the thing to which it is attached does not. The protective current can also come from the mains, solar power, or batteries. This is delivered through corrosion-resistant materials called impressed current anodes. Cathodic protection is used everywhere from supertankers to domestic hot water services. It's used in buildings to protect metal reinforcement in concrete, or underground structures such as pipelines or tanks. An alternative to coating the material is to change the chemistry on its surface through the use of inhibitors, which are widely used in cooling towers, hot water heating systems, engine radiators, and in oil refineries. They stop metal dissolving by poisoning the reaction or by changing the surface to form a protective layer. Inhibitors are also used in primer coatings. Chromate inhibitors give zinc-plated fasteners their characteristic olive tinge. Vapor phase inhibitors are used in storage and transport to keep manufactured goods rust-free. Oxygen scavengers are not inhibitors, but have a similar effect. They are chemicals that remove oxygen which can cause corrosion from boiler water or water in storage tanks. Dehumidification or removing water from the air will also stop corrosion. Silica gel is often used for this purpose. Polymers are being used more frequently as alternatives to metals, although their strength, temperature limits, and solvent resistance means they may not always be suitable. Composites using metal or ceramic fibers in a polymer matrix can offer more strength and chemical resistance. Increasingly, materials such as carbon fiber and polymer are being used in masts, aeroplanes and car components instead of aluminium or steel. Some of the new forms of protection are also the oldest. Roman gladiators, when they went fighting, sheathed their iron swords in sheep's wool, protecting the surface from corrosion with lanolin. The grease you see on winches isn't just there to lubricate. It's also there to keep air and water away from the cable and other metal parts, particularly when they're being stored. These primitive protection measures have now become extremely sophisticated, but the principle remains the same. Hot wax, resins, and similar materials are all used as temporary protection systems, particularly while materials are being stored. Silanes and siloxanes were developed in Europe to protect statues from the effects of acid rain. They're also used on buildings, bridges, wharves, and to keep water and salt out of concrete, protecting the metal reinforcement. Everything needs protection, but particular industries raise particular protection issues. Electric trains and trams leak current into the ground, which can corrode buried pipes. The electrolysis boxes which sit next to railway lines perform a vital function, monitoring the flow and draining the current away. The marine environment is so hostile it requires the full range of corrosion protective measures: paint, galvanizing, cathodic protection, and massive reinforced concrete pilings and slabs. Yachts and ships require constant maintenance above and below the surface. The light alloys used in aeroplanes, such as aluminium and magnesium, suffer corrosion and need protection by coatings or changes in the surface. They are particularly vulnerable at edges, corners, or around fasteners. Galvanic corrosion can occur if these alloys are put in contact with steel or graphite, as in carbon-loaded washers. Aeroplanes accumulate salt and corrode unless they're thoroughly washed. Even engine blocks can corrode from corrosive elements in the fuel and condensation of water vapor. Construction and building requires adequate concrete cover over metal reinforcement and care on detailing joints and seals, as well as design that allows cleaning and maintenance. Pipelines for water, gas and oil need cathodic protection and coatings on externals. They need to be kept dry internally for gas and oil. Inhibitors must be used if gas or oil and water are mixed. The Roman Empire fell, some say, because its people were poisoned by their lead pipes. When it comes to the purity of our water, we take no chances. Steel pipes used for drinking water are coated on the inside. They also have exterior paint and sleeves. Our reservoirs are protected. The correct material is used for taps. The smallest defect can let corrosion begin its work. Corrosives can be trapped by crevices, upturned hollows, in undrainable bottoms of tanks, under insulation that is not protected from rain or spills. The tiniest defect can eventually bring a great project crashing down. Everything can be anticipated by designers. Engineers, builders, architects and planners must ask the right questions. What are the atmospheric conditions? What is the proximity to the sea or an industrial site? We can map corrosion and the expected rate of corrosion in most parts of the world. What temperature will the plant operate at? Will it run continually or switch on and off? What is the possibility of aggressive trace contaminants accumulating? What health issues need to be considered? In other words, what methods of corrosion control are most effective for the life of the material which needs to be protected? Coatings, cathodic protection, more resistant material, polymeric material, inhibitors, or a combination of techniques. It is not just the design of buildings and equipment that is important. The protective material must also be designed carefully. Consideration must be given not just to the chemistry, but also to practical matters, such as its application. In other words, we must make sure the lining sticks, the protective layers do not shear off, and the coating is thick enough. Earth, air, fire, and water. The old elements of the alchemists are constantly at war with each other and with us. Each in his own way works to bring down the things we build. Everything eventually will corrode. Even Teflon can be corroded by ozone. That is why there will always be work for those who join the fight against corrosion. More technically advanced societies create more complexity. There's a greater need to protect our assets, and more assets that need protection. After all, corrosion doesn't just operate on a grand scale. It isn't just dams and skyscrapers. Microchips also corrode and need protection. Furthermore, as we value the things of our past, they too must be protected. Sydney Harbour Bridge is well over 70 years old, a vital link in Sydney's transport system and a major tourism drawcard. Sky Tower in Auckland is the tallest tower in the Southern Hemisphere and has become a potent symbol for the people of New Zealand. We are protecting these iconic structures for future generations and keeping them safe for ours. We play a vital role in our society. We protect the things our communities value, but which they also take for granted. We're in the wings of huge aeroplanes, in the hulls of supertankers, aboard aircraft carriers, inside engines. We're in bridges, pipes, beneath railway tracks. We work on steel, concrete, timber and plastics. We're there because there is nothing that cannot, one way or another, be corroded by something else. By water, sunlight, friction, acid, or time. We can stop it. We can always stay one step ahead. These days we hear talk of all sorts of literacy. People are said to be computer literate, financially literate, and the process of resisting corrosion has become so complex, so challenging, and so important that it now seems appropriate to speak of people who are corrosion literate. People like us, the members of the Australasian Corrosion Association.